Alright, greetings, attendees of the Emi Viola Student Science Conference. I would be presenting this in person right now, but I'm leading a robotics team that's going to an international competition in DC, and they wanted me to be there for some reason, so I wasn't able to make it to the conference, fortunately. This project that I'll be covering originally was meant for district and then state science and engineering fairs, so it's really more of an engineering project, which I know isn't quite what this conference is meant for, but whatever, close enough. Regardless, I'm Michael Quinn, and I'm pleased to present to you Into the Deep, developing an ROV for mapping the mesophotic zone. Alright, bit of background first. This is a mesophotic coral ecosystem, MCE. There are a few of these around Hawaii, as well as a bunch of places in the rest of the world. These are really deep down, so they're really hard to study, but are super healthy and have a lot of potential. Connected to that, this is a 3D map of a reef created by a method called photogrammetry. To make one of these, you take a bunch of pictures, give it to a computer program, and you get a 3D map. They're super useful for studying reefs and for conservation, but because you have to take so many pictures to get an actual map, they're really time-consuming and difficult to make. Because of that, very few have been made for MCEs in general, and none have been made for the ones in Hawaii. So that's the project then. Design and build a remotely operated vehicle, ROV, to descend to these reefs and create 3D maps of them. This dodges some of the problems in accessing these reefs on normal diving methods. So that gives these design objectives. The ROV needs to have a 50-meter depth capability, the ability to make maps using photogrammetry, and high underwater endurance so it has time to make the maps. It also should be easy to build and control so it can get distributed easily. In addition to that, operational procedures to use the vehicle should be developed in conjunction with it. Okay, keeping those things in mind, this is the design that I created, the version 1. It's designed around these two main enclosures that house all the electronics. Seawater and electronic things don't get along very well, so they have to be isolated somehow. The enclosures are rated to 100 meters depth, which is plenty for this project. It's powered by 5 thrusters, 2 horizontal and 3 vertical, giving it control in nearly all directions except for moving laterally. Attaching everything together is the frame, which is fully 3D printed. All parts are also small enough to fit on most 3D printers available, anything with a 235 by 235mm print bed or larger. In order to do photogrammetry, this design has 3 cameras, one looking forward, one looking down, and one looking to the side, which is inside the lower enclosure, not including an additional internal camera for navigation. Controlling the ROV is a system based on the Ardusub control system. This control system is sort of like this. So on the surface is a laptop running Q-Ground Control, which is the control software, with a gamepad. This is what you use to control the ROV from the surface. Connected to the laptop is the tether, which runs down through the water to the ROV, so a physical connection is necessary for this. On board the ROV, the tether is connected to a Raspberry Pi. This interprets the control signals from the surface and sends a live camera feed back up the tether, as well as a bunch of other data for navigation. The Pi also sends control signals to a Pixhawk 1 drone autopilot, which uses a bunch of sensors and math to stabilize the ROV and make sure it doesn't go out of control. Testing of the full vehicle was unfortunately rather limited. Only a few full function tests were performed. However, it was demonstrated to be capable of producing photogrammetric maps of the seabed and descended to 15 meters or about 50-foot depth with no issues. It was still lacking in a number of areas, however, most notably of which was its poor bottom time of only around 15 minutes, the goal was 45, the mediocre quality of the map that it made, as well as some major structural problems. So after basic function tests, in order to better understand and refine parts of the vehicle, testing was broken into 4 major sections method selection. That way, each of these separate parts can be more scientifically tested individually to find the optimal result. First off, the thruster improvements. So one of the initial requirements, remember, was for the vehicle to have high underwater endurance. And in order to get that, it needs to have high battery capacity and needs to make use of those batteries as efficiently as possible. Higher battery capacity is simple enough, just add more, but efficiency isn't. But one way to conserve power is by making these thrusters more efficient, which is the main consumer. In this case, that's going to be done by optimizing the number of propeller blades that each thruster has. 2, 3, and 4-bladed versions of the propellers were tested on a bench measuring the speed of the water that the thruster put out. Being given the same amount of power, the 2-bladed propeller produced the most thrust, which makes it the most efficient. Again, optimizing for high endurance, another source of inefficiency is hydrodynamic performance, essentially how streamlined the vehicle is. Think aerodynamics, but water. With water being more than 800 times denser than air, this has a major impact on efficiency, and the first prototype was not designed with hydrodynamics as a priority, and thus likely has very poor performance. A completed 3D model of the vehicle was evaluated using a computational fluid dynamics simulation. Areas of poor performance were found behind the forward vertical thrusters and behind the main enclosure. While building the ROV for the initial tests, a main structural spar shore completely off. A major part breaking like this before testing even began is definitely not good, so this needed to be fixed somehow. This possibly could have been due to the type of plastic that was used. Test parts were 3D printed from 2 different types of plastic, PLA, which was used for that part that broke, and PETG. These were masked, then tested to failure on a bridge test bench, which just keeps adding load to the part until it breaks. Some failures of these parts were more interesting than others. This one exploded. This one just kind of bent a lot. Guess which one I managed to record. Riveting. Moving on, PLA was found to be lighter than PETG, but PETG was significantly stronger and thus was more structurally efficient, so moving forward, frame parts are going to be made out of PETG. When the first 3D map of the seabed was created, a number of data gaps in the map were identified, partially due to a lack of image overlap. So, different patterns of moving the camera over the target area can give better image overlap, so this is what was tested. 2 mapping methods were tested. Mowing the lawn, which is kind of moving back and forth over target area, and the circle method that we called it, which moves over the target area in concentric circles, kind of in a spiral, with the help of a rope and spindle at the center. Each map was evaluated on 5 criteria: data fill, image quality, time to take the images, and time to generate the map, and the overall area that was mapped. These all were put into a weighted analysis table. Can't exactly get into how it works for the sake of time, but it essentially is a way to combine a bunch of different criteria into a single score to evaluate how effective a method was. So from this table, the circle method of mapping was found to be the most effective, and a modified version of it should be used for creating maps in the future. After testing concluded, a full second version of the vehicle was designed, mainly based around more internal spacer cameras and more battery capacity, as well as hydrodynamic optimizations and some other improvements. However, this was not able to be built in time. In conclusion, this project has covered the beginnings of the development of an underwater ROV for performing photogrammetric mapping on MCEs. Initial testing revealed that the vehicle that was designed was underperforming in some critical areas. Additional testing was then broken up into multiple sections to more scientifically test individual components. While no vehicle was created that adequately meets all the design requirements, the testing that was performed here can lay the groundwork for future iterations on the ROV that will. While this project might seem limited in applicability, the potential it could have is enormous. So, easing some of the difficulties associated with studying MCEs could lift the curtain on a lot of mysteries that exist at these depths. Additionally, the maps that it creates could be used for new avenues of study as well as conservation that were just impossible beforehand. Looking beyond MCEs alone, the ROV could also be used for shallow water marine research and could be easily applied to a number of other fields. Alright, I think I've rambled on long enough. This is normally the part where I would ask if there are any questions, but that doesn't really work out here, does it? Anyways, thank you very much for your time.